Oh, no sound. Okay, wait. Have. I have sound. Don't scare me. I have sound.
Mr. Lu, can you do a front flip instead?
No. Okay. Yesterday I mentioned something about the atomic size, right? Yes. If you can recall, I said going down the group. Okay, I need one with going down the group. Okay. Okay, going down the group of the periodic table. Okay, for example, lithium, sodium, potassium, the atomic size increase, right? Then I mentioned something about more protons inside the nucleus. Rubidium. Okay, the answer is not completely correct. So I need to address that in case you think that's the only reason. Okay, so this is actually a JC concept lah. So just afraid that you confuse yourself. Okay, so when you go down, yes, it's true that inside the nucleus, right, there will be more protons added. Okay, so now the question is, when I add more proton, what happens to the overall atom? In terms of the charge, the positive charge. I'm adding more proton inside the nucleus, right, from here to here to here. I'm adding shells now. As I add shells, my proton number also increase. Right, 3, 11, 19. What happens to the positive charge inside the nucleus? Increase or decrease? Increase, right? Because more proton is positively charged. Okay, so as you go down the group, okay, naturally the positive charge of the nucleus increase. Okay, however, that is not a direct. It doesn't directly affect the size. Okay, I think yesterday I said because of the number of protons inside, it affect the size. Okay, it's not a direct correlation. Okay, so example, let's say I have lithium. Okay, lithium, how many protons? Lithium, how many protons? 3. So 1, 2, 3. Is that right? Then of course I got neutron also lah. How many neutron? Okay, I'm not focused on the neutron, I'm focused on the proton only. Okay, sodium, how many protons? Sodium 11. Then I'll have 11 plus inside, right? Yeah. Okay. Let's imagine there's 11 times 11. Okay. So as I go down the group, notice that the proton increase in the nucleus. Okay. Therefore, the total positive charge increase. It's still plus, but more increase charge. Okay. So this doesn't affect the size directly. So I take it back. Okay, if you really want to know all the factors that affect the size, then you wait till JC. Okay, there's a lot of factors. But in general trend, as you go down the group, the atomic size will increase. That means the size of the atom. Okay, just in case it's standard for you. Okay, the three of you following, right? Okay. Stop, following. No. Okay, sorry. Okay, I clarify. The number of protons inside the nucleus doesn't directly affect the size. It's not because of more protons, therefore the size gets bigger. Okay, the size gets bigger mainly because of the shells, right? Number of shells is increasing. One shell, 2 shells, 3 shells, 4 shells. Okay, that is the main reason. Okay, but there's a lot of factors. Therefore, I cannot tell you, I cannot say that this is the only reason. Okay, other factors besides. Okay, I don't want to go into it. Okay, so you wait till JC or you see your database question come out, then you deal with it. Okay. Okay, I'm going to carry on with. Okay, so I already checked this. So yesterday the confusion about this, right? Okay, if I'm not wrong, the textbook got issue lah. So that they are asking about charge on ion. So please remember, there's supposed to be -3. Non-metals will form ions with -3 charge as well. So for example, nitrogen will form Na3-, then phosphorus will form T3-. Okay. In fact, I don't know why they put this. Okay, I think the reason why they put this is because phosphorus can also form covalent bond. Okay, so in this case, can you tell me what is the oxidation state of phosphorus? Is -5. -5. +5, right? Cl is -1. Remember, group 17 based on the rule. Okay, they will take -1 OS. Okay, then you have x, let P be x plus minus 5 gives you 0. Therefore, phosphorus will be plus 5 in this case. Okay. Okay, then I think the rest should be okay. Okay, so metalloids I covered already. I talked about metallic character. So metallic character is always in terms of how easily the electron is lost from the atom. So the further away from the nucleus, okay, in other words, the more electron shells I have. Right? Okay, sodium has one more electron shell than lithium. Therefore, the valence electrons, okay, of those who further down in the group are further away from the nucleus, more easily lost. Therefore, higher metallic character, okay, or you can say lower non-metallic character. Okay, metalloid. Okay, so yesterday we talked about group 1 trends, right? So please remember when we talk about alkali metals, okay, you need to be able to quote the properties. Okay, so in general, alkali metals soft and can easily be cut with a knife, low boiling melting point compared to other metals. Okay, please do not say they have low. Okay, I think it's a bit big here, but it's in relative to other metals. Okay, low density they float in water. Yesterday I already showed you the video, right? They will float on the water, then they will like move around, right? Because of I don't know whatever the physics side, okay. Okay, energy, I think they use it for momentum or whatever. Okay, so remember the trend. Okay, so we say density increase down the group, which is why only the first 3 can float on water. Okay, then vice versa. Density down the group increase. Okay, as then melting point down the group decrease. Do not mix up the trend. Okay. Okay. So yesterday I stopped over here. Okay, alkali metals are reactive. Then yesterday I said, okay, remember this reaction. How do we get our alkali, right? For example, our sodium hydroxide, potassium hydroxide, okay, even your lithium hydroxide. Okay, lithium hydroxide, remember, it's also considered alkali because it's a group 1 alkali. As long as it's a group 1, it is always soluble. Okay, so soluble base is an alkali. Okay, so how do you get it? Your reaction is simply your metal plus water into your hydroxide plus hydrogen. So this one, please revise your balancing. Okay, you always start with the metal. Okay, so in this case, we are looking solely at your alkali metals in group 1. When you add with water, you form hydroxide. Right, notice what is special about all the hydroxide? Similar chemical equation. Similar formula. Because the way to write the formula is based on the chart, right? You have Li plus, OH minus, right? Same thing, you have Na plus, you have K plus, then you have whatever below. Okay, everything is plus 1 charge. When I form a compound with hydroxide, ionic compound, the formula looks exactly the same. Okay, so in that sense, if you think about it, the balancing will be exactly the same as well. Okay, only the formula is changing. So if you do one, you can do all, right? So if you start, let's say we just do Li plus H2O, you must remember everything we learned last year. So in this case, you know that hydrogen will be formed. Okay, based on the word equation. Okay, hydrogen must be H2. Why H2? Why cannot write H? What's the result hydrogen? How does H alone, how does it look like? One electron, right? Then? Okay, so it must share, right? Then it becomes stable, right? So hydrogen, same thing, right? All your diatomic molecules, you must remember why they exist like that. So same thing as you can go to the extend to the others, right? Oxygen, why is it? Because oxygen alone has 6 valence electron, right? Oxygen is not satisfied. It has 6 valence, so it will share. Okay, oxygen has 6 valence, so it will share 2 electrons. Okay, maybe I do the other side. Okay, oxygen has 6 valence, it will share with another oxygen atom to form O2. Same thing, nitrogen, how many bonds? A triple bond. Why triple bond? Why triple bond? How do I know nitrogen is triple bond? Memorize it. What tells us that nitrogen will form triple bond? What is the idea that we use to tell how many bonds they form? What's the term for? Valency, right? So you just need to think of valency. Nitrogen, what's the valency? No, that's a good number. Nitrogen valency is, and it's not good copy. Okay, valency 3 means can form 3 bonds. Okay, if nitrogen were to form a bond with another nitrogen atom, both can form 3 bonds. So they have to form a triple bond with each other to satisfy this. Okay, oxygen, what's the valency? 2. So I must form a double bond with another oxygen atom. Then I can achieve 2 octet configuration. Okay, so if you use valency idea to bond on this, there's no need to go and do math and calculate. Okay, I don't need to think, hey, how many more electrons do I need to share to achieve this by octet configuration. I just go by solely by valency. This valency concept, please remember, because when we move on to organic chemistry, all these must know, because organic chemistry is all built in non-metals. Okay. Then last but not least, your hydrogen, because only one bond, I no choice. I have to bond, share 1 electron with another hydrogen atom. Okay, so this can be extended to your chlorine, your bromine, fluorine, everything is the same concept. The reason why they exist as diatomic molecules instead of monoatomic or triatomic. Okay. So if I have hydrogen already, remember how do we? I'm recapping all the set 3 things as we go along. How do we write the balance equation? Let's say I chose this. Okay, we start from scratch. How do we write the? Okay, I write here lah, so the recording here. Let's say I start from scratch. Wow, I messed up. I forgot to share screen. Oops. Okay, please find some space. How do you write this from scratch? I know that my metal. Okay, metal, how do we write the chemical formula for a metal? Let's say sodium. Why just write Na? Why write Na? Why not Na plus or whatever else? Okay, Na, why? Okay, so as in, okay, for Na, what kind of bonding? No, it's not ion, it's a metal. Metallic bonding. Yeah, so metallic bonding, how is it? What is metallic bonding? It's between what? It's the bond attraction between what? I know metal lah, but within the metal itself, right? Cation and what is the cation for sodium? What is the cation that sodium forms? Na plus. Then, and what else? The electron. This itself, this thing here, this represents your metallic bonding. It's between the sodium cation as well as the C of delocalized electron. Can you remember or not? The metallic bonding will look like that. You have a lot of sodium ions. Okay. Okay, then you have a C of between the C of delocalized electron, right? Something like that. I can do like that lah, huh? Huh? 第二声. Oh, you on this one, is it? Okay, something like that. This will be your metallic bonding. So this, the reason why we write as Na is because within the sodium, you can see that sodium metal itself is consists of metallic bonding. Okay, so this is essentially these two together. That's why we can just write this. We don't write just the ion. Okay. I think this. But what do you mean? If the question asks me write sodium ion, then I write this one. Okay, how is a sodium ion formed? When a sodium atom loses electron, right, then I form the sodium ion. In that case, if I form sodium ion, then it's just sodium ion. That this electron is non-existent already because the ion is already formed. You get what I mean? Okay, there's two ways to see this. One is if I the metal itself. If I give you a piece of sodium metal, right, and I ask you write the chemical formula, you will just write this. Because within the sodium metal itself, right, if I have a sodium metal, right, a piece of sodium, I don't know how do I draw sodium. It's just a piece of sodium metal, right? This sodium metal. This is the equation that represents how the metal is. But now if I were to say I use the sodium to form a compound, right? The sodium contributes the ion. Then it's the ion itself because the electron has already been lost elsewhere. Right? When I form a bond, I'm contributing the electron. That's why I form a cation ion. But in this case, the sodium is existing by itself. Is this electron lost out of the sodium? Where is this electron? It's still inside the sodium metal. Do you see the difference? This is still within the sodium metal. This electron still exists within the structure of the sodium metal. But if I form a compound, that's your question, right? If you form a compound, only the ion is contributed. The electron will be used to do something else. That's bonding, right? Bonding is the transfer of electron of sharing. Okay? I hope that clears things. I think the EOI some of you mix up. Okay, you like for metal, you write the positive charge. Okay, so starting, let's write the. Okay, so sodium plus water. Right, water formula, this one straightforward, H2O. Okay. Okay, then NaOH because Na plus and OH minus. Yes, I'm writing the balance. So I'm showing how to start from scratch, how to write balance equation. Okay, NaOH plus what? Hydrogen, right? Formula H2. How to balance this? Which side has more atoms than the other? Right hand side got more. So I must top up where? Top up everything. Okay, I'm missing hydrogen on the left, right? I have more hydrogen on the right, so I need hydrogen on the left. Yes, yes. Then what do I need to do? I times 2 to where? I times 2 to H first, right? If I times 2 here, is it? Then I need to times 2 here. Okay, then I times 2 here. Then I check. Balance already, right? Okay, so when you balance your equation, you need to have a strategy. It's not anyhow put the number one, then you pray, everything balance out. There has to be a sequence. The reason why I write 2 here first is because I know the left hand side is lacking hydrogen. So I top up first. Okay, I go 2, then because now I have 2 here, I have 2 oxygen. Right hand side only has 1 oxygen. Go and times 2 here. Okay, once I times 2, I realize hydrogen, oxygen all balanced. Left, sodium. Okay, then sodium I top up here. Done. Okay, so if you apply this same method to any balance equation, it should work. Okay, I know some are more complicated, some got six substances or something. Okay, but in general rule, if you do this method, it's quite straightforward. Yes, it's already here. Everything is here. I'm just showing you how to get it. Okay, get it. Okay, so I repeat, it's the same thing for the sodium and potassium. I'm only swapping the metal. Okay, what do you need to know for here? Where am I? I'm this side. Okay, so what do you need to take note for this side? Beside the equation, you need to describe the intensity of the reaction. Okay, so if the question asks you, what do you observe when sodium react with water, then you must write react violently. Okay, all these. Okay, I think this is the perfect answer. Perfect answer will be all these. Okay, but if you but the key focus is where? Is on the intensity of the reaction. Okay, so react quickly, react violently, react very violently. Okay, sound very ridiculous, but they are trying to show in terms of increasing intensity, right? Okay, why is the reactivity increasing? Because of here, remember, the further down the group, okay, the more electron shares you have, which means the valence electron is further away from the nucleus. Okay, therefore it's more easily lost. Okay, when I lose my electron more easily, I'm more reactive. Okay, so that is a general rule, right? When the more easily an electron is lost, the more reactive the metal is. Okay, later on, next chapter is on metals already. So you will see this again when we talk about reactivity of metals. And we're going to compare across all the different metals. Okay, any questions on this so far? Okay, reactivity increase as the group goes down. Only for here. Okay, only for group 1. Okay, why I say only for group 1? Because it's totally opposite. Okay, so now your group 17 is called your halogens. Okay, take note of the name. Sometimes they will just refer the halogens. No, different. Okay, halogens group 17. Okay, they are your non-metals and they exist as diatomic. Why diatomic? Same explanation as just now. Okay, but the bonding is slightly different now. Okay, how many valence electron group 17? 1 valence. 7 valence. So for example, chlorine, I'm only drawing valence shell. 7 valence. Is chlorine happy or not? Not happy. So you go and find a partner. Okay, you go find a partner to share electron with. Okay, then now you have chlorine, Cl2. Same goes for F2, Br2, I2. Okay, At2 also. Okay, the whole of group 17. Okay, that's why there is diatomic molecules. Why low boiling melting point? Don't tell me it's a gas. Okay, simple molecular structure. So what? Big intermolecular. Big what? Big intermolecular forces of attraction between molecules. Okay, between molecules, then what? Okay, right here. SFS. Weak intermolecular forces of attraction. I short form, I write FOA. Between molecules. So what? Small amount of energy is required to overcome these weak intermolecular forces of attraction, therefore low polarity. Okay, very sequential one, the explanation. Okay, the color is not a chemistry reason, it's the physics part. Okay, why the color? You know, color is from physics. It's light. Absorption of light and
So what can you name the spectrum?
What do you name the spectrum? It's from it's the rainbow lah, the rainbow.
Yeah, so what is the acronym?
ROYGBIB.
Very ugly extra.
ROYGBIB.
I know.
The one is the same.
Huh?
Sorry,
Because it reflects blue light.
No, it's because it's the special.
Okay, next trend. Do not, I repeat, when you study this chapter, please get the trend right. One trend wrong, then when you get a trend wrong, then the opposite will be wrong also. Okay, for halogens, notice down the group, melting boiling point increase. Is it same or opposite as group 1? Is it the same? No. It's opposite of group 1. Group 1 is down the group, melting boiling point increase. Right? Okay, so it's opposite. Must remember the trend. Okay. Down the group, color intensity increase. Okay. color must remember, please use the textbook appearance. I mean this color. So don't give me reddish brown, brownish red, browny red, red and brown on your own color. Okay, please use red, brown, yellow, green, purple, black. I think last year we did teach yellowish green, right? Okay, I tell you what, let's stick to this. Let's stick to this now. Okay, because this in your textbook, we just follow, okay? New syllabus. Okay, so you see, melting boiling point is clearly increasing down the road. Okay, no, I mean nothing to question here, right? Because it's a trend. Okay, this one, take note. Down the group, reactivity decrease. Is that the same or opposite as group 1? Opposite also. So if you think about it, group 1, 17, your trends are reversed. They are not the same trend. Okay? Down the group, reactivity decrease. Which means what? Which is the most reactive group 17 element? Fluorine. Okay, starting from fluorine, going down, fluorine, chlorine, bromine, iodine, right? Going down the group, reactivity decrease. Okay, displacement reaction, learn before. Did we learn displacement reaction? We did, right? We did talk about displacement. Okay, what is the displacement? I think the definition is really written here. You have one element taking the place of another. Actually, right? Your displacement we did cover what? Which chapter?
Sure.
Acid base? No.
Well,
Summer.
I mean,
Okay, which chapter? Your QA, right? QA, where is the displacement in QA? Why QA got displacement? Your QA is the OH minus, right? Remember, you add the OH minus, then you form the colored compound, right? The insoluble product. Okay, that one is also displacement. Okay, but never mind. If you can't really recall, we will look at exactly what are they talking about here. Okay, so when you talk about halogens, right? Because halogens have different reactivity, right? Going from fluorine to chlorine, bromine, iodine, ester, what's below 13 and 4, right? Okay, so when you start from displacement, what it means is that the more reactive halogen can always displace the less reactive halogen. So if you think about it, which halogen can displace the rest? Always displace the rest. Fluorine. Then which is the one that is least likely to be is unable to displace more is the one at the bottom, right? Okay, but usually where we stop, we just stop at iodine. Why you want more? Okay, the first 20 elements thing is only drawing the electronic configuration, but we can test you beyond. Okay, but what? Okay, if I were to ask you to draw iodine, you draw for me. Iodine has what? What's the proton number? 50 something, right? Yeah. Can check. 53. Your 288 thing, right, will not work for iodine because one of the shells has 18 electrons. I mentioned before, I think, right? Okay, the 18 thing, why? Because your syllabus only learn until max 8 in a shell, but actually each shell can hold max 18. In the later shells, and this period 3 and beyond, you can hold 18. Okay, just FYI, in case some of you are, your mind is always, remember in the, I also, I think the EOI paper, we also tested the xenon, I say it extends, sulfur hexafluoride, right? Okay, remember it extends beyond octet. Okay, and that is one of the examples, because it's in a later period, it can hold more electrons, so it goes above 8. Okay, which is why we cut at 20. If I get you to draw the electronic configuration of bromine iodine, you will get lost. The numbers will not add up. Okay, so what is displacement? Example, we say chlorine is able to displace. Okay, when we talk about displacement, right, it's always reaction of your halogen with a salt containing a halogen. Example, chlorine reacting with potassium bromide. Okay, so this is the halogen, this is the salt containing a halogen. What's the salt? General. What is the salt? What kind of compound is the salt? Ionic compound. So it's just an ionic compound containing your halogen. Okay, and then usually in this case we just bond with group 1 metal. So very straightforward. Group 1 metal bonded with group 17. You're rushing homework today. Okay, can you focus first? You do it after. Okay, so in this case, we have chlorine reacting with potassium bromide. So chlorine okay, does it make sense if I say chlorine react with potassium chloride? Doesn't make sense, right? Why? Do you even think it will react? It won't react because it's the same. You are trying to displace, right? If I got the same halogen, right? Nothing will happen. Okay, so make sure the halogen must be different. Okay, that's why here is balanced out now because chlorine cannot displace chlorine. Doesn't make sense. I won't react with two of the same halogen. Okay, for potassium bromide plus chlorine. Okay, remember chlorine or bromine, which one more reactive? Chlorine is more reactive, right? Because your reactivity decreases down the group. Chlorine is higher in the group than bromine. So chlorine is able to displace bromine from its solution or its salt. Okay, salt solution, right? Why is KBr soluble? Why? I mean, sorry, it says soluble. Why soluble? Why not? There has to be a reason. It's not because I say that it's soluble. Spar salt. KBr, right? Spar salt. Yeah, okay, just there, but it's a cation ion here. Okay, so in this case, I have chlorine plus potassium bromide. Chlorine is more reactive. Chlorine can kick this guy out. That's immediately kick him out. So when I kick out, I'm replacing the guy. I replace the bromine. I form KCl. Okay. So potassium bromide becomes potassium chloride. Okay. When I kick the guy out, the guy go where? Go home lah. Okay lah. He has to do something, right? To go somewhere. So where he go? Okay. Okay. Maybe I show you how. If I draw it like that, it's easier. I have chlorine, right? Everyone knows why chlorine exists like that. Because diatomic molecule, chlorine plus KBr. This. Okay, it's not a molecule. This one is not a molecule. I just draw like that so you can follow. Okay, so what happens? I chlorine come in, right? To kick this guy out. Then I get KCl. Okay. Then I have Cl, the Br to go somewhere, right? Okay, it's actually 2 KBr. Don't write this, I'm just showing you how it works. Okay, so you have the Br, right? 1 Br. Then of course must balance, right? Because this is not balanced. So 2 here. Then I have 2 Br. The 2 bromine will come back and combine, and then they will form a molecule. Huh? Oh yeah. Okay. Okay, I'm showing you the idea. It's not really like that. It's the same idea as the balancing. Just not how I write one. Can you see it's all 2 ma? Okay, but the idea is here that chlorine comes in to displace and kick out the bromine. Okay, so it's basically you can take of it, they just swap place only. Okay, bromine replace chlorine, then chlorine replace bromine. Okay, keep in mind this only works. This reaction only takes place if the halogen, right? The halogen you are using is more reactive. If it's less reactive, what happens? No reaction. Okay, so if you read this table and you read across, as long as my halogen that I'm using is more reactive than the halogen in the salt, it can kick it out and then the displacement reaction will occur. If it's not, so reverse. Okay, in this case, if I'm trying to use bromine to displace chlorine, can or not? Cannot, because chlorine is more reactive than bromine. Or you can say bromine is less reactive than chlorine. So therefore, this has no reaction. Cannot happen. Okay. So likewise for bromine with bromine, we don't say that because no point. That's why this diagonal is colored in red. It doesn't happen. Okay. I mean there's no point. Okay, then this one why no reaction? Because iodine is the least reactive here. Iodine is unable to displace chlorine or bromine from their salt. Okay, clear on all this? Then if you look at the formula, right, it's exactly the same. The way to balance is the same because the formula that we write for your halogen is all the same. Cl2, Br2, I2. Therefore, when we write the balance equation, right, it looks exactly the same. Okay, however, what is the main difference here? It's the color. Okay, why is the color important? Why is color important for us? Okay, so you can identify that the correct reaction is taking place, right? When you go and do your O-level practical, do you know what the substance is? Everything is labeled A, B, C, D, E, F, G. Okay, you need to be able to identify what is happening. So you have to observe color, right? Remember last year when we talked about QA, what are we looking for? Color. We look for gas produced, right? All these kind of things. Okay, so same likewise here. If I see red brown forming, I will know that the halogen being displayed is bromine and it's not chlorine, it's not iodine. If I see it's brown, I know it's iodine. Okay, if I see it's yellow, light yellow, then it's chlorine. Okay, they basically didn't include chlorine. But you can add in chlorine. So if chlorine were to displace potassium, okay, I'm sure you have to imagine a bit. I use chlorine to displace potassium chloride. Can or not? Can, then I form Kf plus Cl2. Okay? Okay, then you balance. Okay? Same thing, okay, but chlorine isn't in your syllabus, so you don't need to know the color. Okay, so you just know chlorine. So here I will see yellow, green gas form. Okay, so if the gas has color, then you can also identify. Okay, so using the color observation, okay, I can see. Okay, it should be equals. Sorry. Okay, why is it equal instead of gas? Because it's happening in a salt solution. Therefore, it is not. Okay, I'm going to stop here. Okay, okay, so next week for lesson, can I get you to bring your TYS? The topical from last year. Please bring. We will do some practice questions because this topic needs a lot of practice one. I cannot just say then nothing go in. Okay, any other question? Okay, please remember to submit your ammonia worksheet to Racing. If you haven't done, tomorrow is the last time. I want to mark over the weekend so I can go through next week. The longer I delay, you cannot revise for your time frame in week 3 time. Okay, so if you don't give me by Friday, today, if not tomorrow, I'm going to delay again. Then the whole class cannot get with me. Okay, they cannot get back the paper. So please cooperate. Okay, class 10.